Hello, everyone, and welcome to Lecture 4 of the Quantum Student Society lecture series. My name is Brady, and today we are going over the Stern-Gerlach apparatus and measurement of qubits. All right, now let's look at our agenda. We are starting off with the Stern-Gerlach apparatus, and then we're going to be moving to measurement basis, geometric measurement of a basis, and the effect of measurement. Let's talk about the Stern-Gerlach apparatus. Now, this is a device that measures an electron to see if it is spinning up or down. Think of ones being spin up and zeros being spin down, like a classical computer where you have ones and zeros. The idea that electrons can spin up and down was discovered in 1925. However, experimental discovery was shown in 1922 using a Stern-Gerlach apparatus. This device was also created in 1920 by Otto Stern and Walter Gerlach. What it does is it takes a measurement, and this measurement that the device takes is kind of like flipping a coin, where it can be both heads or tails when it's in the air. However, whenever you're measuring it and it flips and lands on your hand, then it is heads or tails, which is the measurement. This idea of the two-state property is what is useful and helpful for quantum computers. And to understand what the Stern-Gerlach apparatus is measuring, we first need to understand superposition. Now, superposition is the ability for something to be in two states at the same time. Think of Schrodinger's cat. If you ever heard of that experiment, the cat can be both dead or it can be alive inside of a box. However, it is not until we measure it and open the box that we find that the cat is alive or it is dead. The same thing can be said with the coin, just like the example from the previous slide. There is the coin, which is flipped in the air, and when it's spinning, it is both heads and tails. But whenever it lands and you measure it, then it is one or the other. All right, let's move on to measurement basis. Now, measurement basis is how we are going to be able to understand the measurement of these electrons. So right here we have basis, and that is the direction that we choose to measure the electron, whether it be up, down, left, or right. And then we also have vertical measurement and horizontal measurement. These two measurements detect whether the electron is up or down and also left or right. Now, the key point to get out of this is that while you are measuring the same electron, you have different measurements for it, so you can get different results. And again, we have the coin example, but instead this time we are asking, is the coin heads or tails, or is it facing north or south? All right, now let's move on to the geometric representation of a basis. And the geometric representation of the basis is pretty much the orthogonal states, which are the spin up and the spin down, are perpendicular to one another. So right here we have a spin up qubit, and right here we have a spin down qubit. A spin up qubit has the zero in it. It's very confusing. You'd think spin up would be one and spin down would be two. However, it is the other way around. And so this is the proper representation of the qubit states. And down here, we have the equations, vector equations for each of the qubit. It is important to notice that these two equations, while they look similar, they have that sign difference inside of them. And these equations, the spin up and spin down qubit, we will be talking about them a little more in the future videos to come. So it is important to keep these in mind and understand the difference. Okay, now let's move on to why this measurement matters. And this measurement matters a lot in quantum because if we think about everyday life, if I'm measuring, say, my pencil or my pen, it has a set number or measurement that it is measured to. However, whenever we measure in quantum, not all electrons have the same measurement, and the measurement can be different and it can affect the state of the electron. So if we have a vertically up electron and it is in a mixed state of horizontally, well, a mixed state horizontally means that it's in a superposition of horizontal spin states, and measuring horizontally randomizes the vertical spin. The subsequent vertical measurement also gives us that is up that the electron is up or down with a 50-50 probability. So it has a 50% chance of being up, 50% chance of being down. And this concept is applied in quantum cryptography, where it is used to detect eavesdroppers. And these eavesdroppers are third parties trying to intercept or measure quantum information being exchanged through two other parties. So, this is very important when it comes to protecting your data and protecting the messages that you are sending to people, because without it, then a third party can go and it can see what data you have sent to other people, and that's not good. It helps protect your privacy. So the main takeaway from this is there are often hidden information in quantum states that can only be measured by changing to a different basis. And when you're in that basis, then you can read the quantum state. However, if you are not, then oh well. Now let's go into consequences and applications. Now you can read through all of these. I'm not going to explain them all, but some that I like to point out is the no cloning theorem, which is stating that a qubit in an unknown state cannot be copied, and this is helpful for that encryption in cryptography that we were talking about earlier. Another thing I'd like to point out is quantum advantage, um, and this is the information stored in superposition states allow quantum computers to perform calculations beyond what is possible for classical computers. And this is really good, especially in the future whenever we have fully functioning quantum computers that are used at a large scale. It will help tremendously in both the medical field and cryptography field, which will make it so that medicine is easier to develop and cures for diseases we may not have cures for yet. They will be developed. It's also useful for our cryptography and keeping our information, especially like information about your bank account or money and stuff like that. It'll keep that secure. So the key takeaways that we have are that electrons can only spin in two directions. Um, this is being like ones or zeros in the classical computer. And then electrons can also exist in both states at once. And this is the idea of superposition, thinking back to the coin flipping and being both heads or tails at the same time. We also have how you measure things affects what you get. And this is how we measure the coin. Whenever the coin lands on our hand, we can measure that it is heads or it is tails. And then the strange behavior of this is the foundation of quantum computing and a bunch of the applications it can be applied to. It is very important to understand for the future concepts that we will learn in this class. So I thank you guys for joining me today, and I will see you next time when we talk about quantum gates.